Hi, and welcome to 13.4 Wave Interactions and Phase. In this topic, we talk about basically two things: interactions or interference, and the idea of different points in phase with a wave. And they kind of go in hand. That's why they're linked together in this one topic. But they are separate concepts. So let's talk about each one a little bit: interference, wave interference, and phase. So think about like two material objects and how they would interact. Let's say it's if you hold your pen up and you have a pencil and you like have a sword fight with your pen and pencil and you like attack. So here's one sword and here comes another sword. Clang, just like that. They hit each other. They don't pass through each other. They hit each other because they're made of matter. But the same doesn't really happen with waves. Let's say you have a piece of string and then you put a wave into the string. You like shake it up and down. So now the wave's coming this way. And another person sends a wave going this way. All right. Are they going to clang against each other and like bounce off each other the way the swords do? No, because the swords are made of material or matter. And waves, do waves transfer matter? No, waves transfer energy. And this energy can be like superimposed at one position. So when these two waves eventually meet each other at like, let's see if I can move this. Here comes this wave. Here comes this wave over here. We're trying to move them around. My computer's being super slow. And what happens? How are these two things going to interfere with each other? Well, we have a crest meeting a crest, and what you get is there's only one string, so it's not like you're overlapping the string. What you get is a super crest, an amplitude plus an amplitude. So that's what it looks like there. Okay, so its interference is all about how energy overlaps or superimposes with each other. So that's interference. Let's talk a little bit about phase. So for that was just very brief for interference. So for phase, you have to think of a circle. And how many degrees are in a circle? 360 degrees, right? So if we pick a point right here, and let's say we go around, this is 90 degrees. This is then, we're going around this way. This is 180 degrees. This is 270 degrees right here. Okay. So in a wave, so that's, and then you get 360. That's one full cycle. All right. One cycle equals 360 degrees for a circle. The same could be said for a wave. So let's say we start here. We go up. We go down, back to equilibrium. Then we got to do the trough. And now we're back to where we started. All right, because then the next move is to go up to the crest. So that's one full cycle. And when we're talking about phase, we still use like degrees. So one cycle is equal to 360 degrees. And if you make this your starting position, this is 90 degrees from here. This is 180. It's half of a wavelength, all right, or a half a circle. Half of a circle is 180 degrees. So this is 180 degrees. This is going to be 270 degrees. And now we're back to 360 degrees, or you could say 0 degrees, or you could say in phase. And 180 degrees would be completely out of phase. All right. But even 90 degrees is considered out of phase. But 180 is like totally out of phase. It's the opposite. So that's for like one wave. And then in this homework assignment, they're kind of talking about, well, let's say you have a wave and you want to draw another wave that's like, let's say 180 degrees. Let's start simple. 180 degrees out of phase with this wave. Well, we know that if this is our starting position, then this is going to be 180 degrees out of phase. So what they're saying is start there. So we're like taking this and shifting it over here. So we're going to draw another wave. We're talking about two wave trains and like, are they out of phase or not? And we're going to go down to the trough. So it's now we're starting at that position and then we're coming back up here. And now here it's a crest. And then now it's back to a trough. So these two waves are 180 degrees out of phase with each other. And if they were to interfere with each other, what would happen? You would get a standing wave. Because if this one's moving this way, and this one's moving this way, you would have points where it's always destructive interference and always constructive interference. And then let's talk about what happens if it's 90 degrees out of phase. So if it's 90 degrees out of phase from this point to this crest over here, that means we're going to start here. So we're going to move it and we're going to go right here. So we're starting at the crest, we're starting at the top. And then the next move, the next like 90 degrees is, so from here to here, 90 degrees is going to be at the equilibrium position. So we want to make sure we draw our wave going here. Then 90 degrees from equilibrium is the trough. 90 degrees from the trough is equilibrium again, and so forth. So that the green wave is 90 degrees out of phase with the black wave. Just like that. And you could even have one that's 270 degrees. So 270 degrees out of phase with that goes down here. So you could start in the trough. Then you go equilibrium, crest, equilibrium, trough, like that. And you're going to go like that. Just like that. So this red wave is 270 degrees out of phase with the black wave. This green wave is 90 degrees out of phase with the black wave. And this blue wave is 180 degrees out of phase with the black wave. So it's like a little pretty picture there. So let's do some problems now that we have a little bit of background. So number 1 says the diagram below shows two waves traveling towards each other at equal speed in a uniform medium. When both waves are in the region between points A and B, they will undergo, are they going to do destructive? Are the amplitudes going to cancel each other out? If it's destructive, that means it looks like a trough is meeting a crest. And let's say this has an amplitude of 1, this has an amplitude of 1. When these two things meet each other and they interfere, what's -1 plus 1? 0. So for a split second, there's going to be like no wave there because they cancel each other out. It's destructive interference. But then after they pass through each other, they phase through each other, that crest will be now on the left side moving to the left, and the trough will be on the right side moving to the right. And they'll move through each other like nothing happens. They'll be like, okay, whatever. They'll pass like ships in the night and not even know that they went through each other. Okay, so, but that's not going to happen here because we have a crest incoming with a trough incoming with a trough. So that's going to be a constructive interference. That's going to look like this. We have a trough coming in here, moving to the right. Let's say it's -1. And another trough. Let's say the amplitude is -1. It's being displaced -1, whatever, meters away from equilibrium. When they interfere with each other and like phase through each other, that amplitude will add together. Even though it's down, it's negative, it's going to be -2. -1 plus -1 is -2. And then they'll continue passing through each other. This one that was on the right is now on the left, moving this way. And this one continues moving to the right. All right, so that's constructive interference because the pulse got bigger. It was -1. It was -1. They're working together. They're on the same side of the equilibrium, so it's constructive interference. That's how you can tell if it's constructive. If they're on the same side of equilibrium, if they lead to a bigger amplitude. That's constructive. It's like they're building. Reflections are not going to be part of this because that reflections happen when you hit a barrier. So we didn't really talk about reflections yet. And ducks on a pond is kind of nonsensical. All right, moving on to number 2. Number 2 says the diagram below shows two waves traveling in the same medium. Points A, B, and C, and D are located along the rest position of the medium. So it's saying like originally the medium's like this. This is equilibrium, but then some waves come and mess the equilibrium up. All right, so that's where those points are located. And it says, at which point does the superposition of the waves produce the greatest positive displacement of the medium from its rest position? So these points are happy here, and then these two waves come by. All right, now they're interfering with each other, so these points are going to move. But we have to like add together the waves to see what actually happens. So let's say at point A, this small wave is giving us an amplitude of 0.1, but you also have this second wave coming through here, and at point A, it has an amplitude of positive 0.2. So you just do 0.1 plus 0.2, and you get 0.3. This medium that was originally at the 0 line now is going to be at 0.3 when you superimpose those two waves together. They're interfering now. They're not showing the interference on the graph, but they're showing you the two waves that are going to interfere. So you have to add the amplitudes together. So for point B, the small wave is negative 0.1, and the big wave is positive 0.2 up to this position here. So what's 0.2 plus negative 0.1? That's just going to be positive 0.1. So it's like 0.2 minus 0.1. Then for C, it's kind of the opposite. We have 0.1, positive 0.1, minus negative 0.2 or minus 0.2, and you get negative 0.1. And then for D, it's negative 0.1 and negative 0.2. So what's negative 0.1 plus negative 0.2? That's going to be negative 0.3. So the wave would look kind of wonky, but this is like where those 4 points would be. So the question is the greatest positive displacement. So point A is showing the greatest positive displacement of 0.3 meters. So that's point A. Number 3, two waves having the same frequency and amplitude are traveling in the same medium. Maximum constructive interference occurs at points where the phase difference between the two superposed waves is 0 degrees. And here's why. If you have a wave like this, and then you have another wave that's exactly the same, it's in phase, what you wind up with is, let me make it a different color actually. So we have the black wave, and we have a blue wave that's totally in phase with it. It's 0 degrees out of phase. Well, you have the 0.1 amplitude plus the 0.2 amplitude. And just like before, when we added the amplitudes together, that leads to a point that's up here. And the trough plus the trough, the point that's up here. So the superimposed wave looks something more like that. So this is constructive interference because the waves are adding together, and that happens when it's 0 degrees. Conversely, if you had them 180 degrees out of phase with each other, so now we'll do like the opposite extreme. Then we had a wave. So 180 degrees out of phase means take this starting position, but instead do this first. So 180 degrees here. All right. So we'll do that. We'll draw the trough first. That's showing that it's 180 degrees out of phase. And then we draw the rest of the wave. Well, if we were going to do the interference thing again and add the amplitudes, this is like +1. And this amplitude's like -1. And at every position along the wave train, they're like canceling each other out. Even at here, it's 0 and 0. And here it's negative, and here it becomes positive just as much. And you end up getting destructive interference when it's 180 degrees out of phase. So that's destructive. Here, the black and the blue wave was in phase, or 0 degrees out of phase. The phase difference is 0 degrees, so that's constructive. So that's why it's A. And then number 4, It's saying two waves having the same frequency, blah, 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 blee, blee, blee. It's asking for the maximum destructive interference. So that's that situation that we just talked about, 180. The 90 and the 270 are like slightly different, so it's not going to be maximum. So number 5 says two pulses traveling in the same uniform medium approach each other as shown in the diagram below. I think I need to, hold on a second. This is an old version. Okay, sorry about that. I think I was like in the middle of revamping this old PDF last year, and then I don't know. I'll finish it up, I think. Yours is going to look different from this probably, or it's different from what the rest of this video has been, but the questions are in the same order. So let's continue with number 5, I guess. Number 5 says, two pulses traveling in the same uniform medium approach each other as shown in the diagram below. Which diagram best represents the superposition of the two pulses? So these are like waves, but they're not periodic waves. They don't fall into the simple harmonic motion because it's not like a nice sine pattern. It's this triangle stuff. So what would these two triangles look like if they were interfering with each other? You have to do the same thought process of, well, I have this one here, and then I have another triangle right on top of it. So at this point here, it's also always easier to look at the maximum. So I have that maximum plus that maximum. This maximum is going to be like that plus that. Maybe it'll be up here somewhere. And then if you want, you could extrapolate like some other pieces. So like 0 and 0 is 0. So that amplitude stays there. But at this point, you have this little bit plus this little bit. So a little bit and a little bit is going to bring you to like here and here. So what you should look for is like a taller triangle. And what we get is a taller triangle, choice C. All right, choice D is the same amplitude. It's the same height. So that's not what we would get. And choice B, you would get a square from two triangles? I don't think so. Number 6, all right, so now we have two pulses of equal amplitude approaching point P, but they're on opposite sides of the equilibrium. So we have a crest and a trough, and it says when the two pulses meet at point P, the vertical displacement of the string will be 0. These are destructively interfering. So if this was positive 1, and this is on the opposite side, so it's negative 1, and when they interfere, you add the amplitudes together. So at point P, for a split second, positive 1 plus negative 1, the amplitude will be 0, and then they'll continue past each other like nothing even happened. Number 7 should look like this. It says the diagram below. Now they're two squares. Notice the positive amplitude one is a little bit shorter than the negative amplitude one. So we have to take that into account when we're adding them together. If it helps, you could make this positive 1. And since this is bigger, we'll make it negative 2. It's bigger and it's negative because it's on the opposite side of the equilibrium. So what happens when you do positive 1 plus negative 2? You get negative 1. So at this point right here, when they phase through each other for a split second, it'll look something like that. Choice B. Okay. Now we're talking about phase. So it says which 2 points on the wave are out of phase with each other. So we're looking for something that's 180 degrees out of phase. Or maybe it could be 90 and or 270, but we definitely don't want it to be in phase. So at points A and C, here's A, here's C, and they are in phase. And here's a trick. If it's at equilibrium and you want to, because like point B, that's not in phase. And here's the trick how I could tell. This is like going up. This is going up. This slope is going down. So I know it's the opposite point in equilibrium. So A and C are in phase with each other. They're at the same position in the wave. They're like getting ready to do a crest, getting ready to do a crest. They're one cycle apart. They're in phase. So it's A and C. Oh, A and C would not be it, right? We want it to be out of phase. So how about B and F? So B is here, the slope is going down. F is here, the slope is going down. These are in phase with each other. How many cycles apart? They're 1, 2 full cycles apart. If they were like 1.5 cycles apart, I would say they were out of phase. But since they're full cycles apart and that they're at the same position again, all right, they're in phase. We're looking for something that's out of phase. How about C and E? Oh, no, this is going to be positive slope, positive slope. They're 1 full cycle apart, so that means they are in phase. So that's not what we're looking for. D and G, here's D, here's G. This is going down, this is going up. So visually, I could see they're going to be out of phase. They're at different points in the wave. If we want, we could see how many cycles or waves apart are they. This is 1 full wave. Now we only have a half of a wavelength here. So this is 180 degrees out of phase. All right, so it's going to be choice D. The diagram below represents a periodic wave, at which point on the wave is 90 degrees out of phase with point P. So now we're not looking for a half of a wavelength, that's 180. Half of a wavelength here, that's 180. We're looking for a quarter of a wavelength, or 90 degrees, 360 divided by 4. So we're looking for, this is from equilibrium to trough. That's 90 degrees. So it's going to be choice B. Just to prove it to you, not that I have to because I know you believe me, but that's 90 plus 90 is 180 plus another 90 plus another 90 is another 180. So that's 360, and that brings you back to a point in phase. So you could break the waves up into like quarters, 1 quarter, 1 quarter, 1 quarter, 1 quarter, and that helps you with the 90 degree type ones. It helps to do that. Number 10, the diagram below represents a periodic wave, at which point on the wave is in phase with point P. So again, we have it's at equilibrium and it's like a positive slope. This is at equilibrium and it's negative, so nope. This is at equilibrium and it's positive, so yup, choice C. Number 11, diagram below, transverse wave, which 2 labeled points are 180 degrees out of phase? So is it A and D? A and D are 270 degrees out of phase. Nope. D and F. D and F. How many degrees is this? It's from a trough to a crest. This is 180 degrees out of phase. Oh, that's what we're looking for. Let's eliminate the other ones and we'll come back to that. So B and F, why is it not B and F? B and F is 1 full wavelength apart, crest to crest, right? Crest to crest, so 1 full wavelength. That's in phase. And then we have D and H, that's trough to trough. So again, that's 1 full wavelength. We're looking for something that's out of phase, not a full wavelength. 180 degrees out of phase. We're looking for something that's half a wavelength. So from D to F, this is half of a wavelength, and then you have to do this other part to get, this is 360. This is 360 degrees, or 1 full wavelength. From here to here, that's half of that, right? That's splitting it right in 2. So from trough to crest, that's 180 degrees out of phase. A lot of times it's easy to say, oh, that's 180 degrees. Yeah, sure. But so is here, from trough to crest. Okay? Number 12, 2 waves traveling in the same medium and having the same wavelength interfere to create a standing wave. What is the distance between 2 consecutive nodes on the standing wave? So we didn't talk about standing wave in the beginning really a lot, but this is what a standing wave looks like. I'm going to use this line to represent equilibrium. So you have the wave, and I think in the videos they showed you examples of this. It's hard to draw it, because what's happening here is this point travels here. The medium comes down here. But this point stays stationary the whole time. You could put your finger there and it doesn't move. But these points are traveling back and forth. It's like traveling back and forth. But these points don't move at all. So this one, have you ever like twisted a rope around? Like you swung a rope around and you get that nice little pattern before? It helps with demonstrations. It's hard to kind of show with a drawing, because this should be moving, right? But these points move, 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 move. these antinodes, ooh, antinodes, fancy word. These points don't move. Don't move, don't move, don't move. So this is no motion. No motion, those are nodes. So these points along equilibrium, even over here and over here, let's make them blue. The blue points are nodes. The red points, they're moving a lot here. They're going back and forth. These points here are the opposite of no motion. They're anti-nodes. Anti-nodes move, nodes don't move. So what they're asking for is, what is the distance between two consecutive nodes on this standing wave? So here's a node, here's the next consecutive node. And what is the distance in terms of wavelengths? So here's the node, here's the other node. How much of a wave is from here to here? Only this part between these two consecutive nodes. I only see a crest right now. What happened to the rest of this? This is the rest of the wave. So this is only half of a wavelength. From one node to the next consecutive node is half of a wavelength. That's a standing wave. Nodes and antinodes, okay? Number 13, the number of nodes and antinodes shown. So the nodes are the no motion. Don't forget these points don't move either. 1, 2, 3, 4, 5, 6. 6 nodes. How many antinodes? 1, 2, 3, 4, 5. 5 antinodes. So what choice is that? 6 nodes, 5 antinodes. Choice C. Number 14, similar question. What is the total number of nodes and antinodes? So node, 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 node. So 1, 2, 3, 4, 5 nodes. 1, 2, 3, 4 antinodes. So that's going to be choice C again. And then 15, while playing, 2 children create a standing wave in a rope as shown in the diagram below. A third child participates by jumping the rope. What is the wavelength of this standing wave? Jump back to the number 12. Okay, take a look at the diagram that we did. I'm looking at this right here. So here's the person. Here's the other person, and they're actually holding the jump rope like this. See that similarity there? So how much of a wavelength did we say this distance was? We said it was a half of a wavelength. All right, you only have a crest or a trough there. The rest of the wavelength looks like that. Now we have trough, crest. That's a full wavelength. Okay, no, that's ugly. That's a little bit better, not even really. All right, so if this half of wavelength is 4.3 meters, the next part is 4.3 meters. So we have to do 4.3 plus 4.3 to get one full wavelength, and that's how you get 8.6. Now we have a diagram with 2 pulses, both with an amplitude of +3 moving towards each other. As the pulses meet and are superposed, the maximum displacement of the medium is +3 plus +3, so that's +6 centimeters. Sorry for the confusion with like the different versions of this assignment. I didn't realize until I was halfway through the video. But that happens in life. Sometimes you just gotta, deal with different things as they come up, make the best of it, and I'm sure it'll all turn out fine in the end. Have a great day.